Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello and welcome to Physics with Beth and Beth. I'm Beth and we are in this AP Physics C Mechanics curriculum. It's also your one of your first classes in engineering curricula in your engineering degree plan, I should say, and it's the mechanics piece of that engineering physics, and it is all calc based. So we are in Unit 2 with Newton's laws of motion. Okay, we're gonna let's just back up a minute. In our first video, we did Newton's laws of motion, but then we used unit vectors to solve a problem. Today, we're actually taking that calc piece, as we will in every unit, and bringing it in. And we're gonna talk about Newton's second law of motion, but we're gonna use calculus to solve a problem with our derivative. So here we go. We're just going to get started with second law. We know that the sum of the forces equal mass times acceleration. We saw that in AP Physics 1, and we even talked about that your ma is a force to be dealt with. That sum of the forces, that sigma there, sum of the means sum. Some of the forces can also be interchangeable for net force. All right, but that's the algebra way to do things. We're gonna kick it up a notch here. We know from our first unit in kinematics that velocity is equal to the derivative of position with respect to time, and we know that acceleration is equal to the derivative of velocity with respect to time. So now we can sub this in for acceleration, and we get something that looks like this. Our net force, or our sum of our forces, is mass times the derivative of velocity with respect to time. You can also actually call it, since we would have had a position with respect to time equation here, first derivative is velocity, the second derivative from the position equation is acceleration. So sometimes you'll also see it like this, mass times the second derivative of position with respect to time. They say the exact same thing. This is just taking the derivative of velocity. This is taking the second derivative of position, which is the derivative of velocity with respect to time. We're still not quite to where, in the Principia, where Newton published his laws of motion, we're still not quite up to what it looks like in his journal yet, because we have assumed mass is constant. All right, so that mass we've taken out of the derivative. So here mass is constant, and mass is not always constant. Think about a classic example, that's why we call it rocket science, is as a rocket is going up in the air and has acceleration, it is burning fuel, so the mass is changing as it burns its fuel. So anyway, but we'll worry about that another day. Let's just do one thing at a time. So here we go. Let's get started. We have a problem here that says we have a 0.50 kilogram object that has motion described as this. The position as a function of time is 3.0 t cubed plus 2.0 t squared minus 4.0 t, and that of course is in meters. All right, so first of all, we're taking these derivatives with respect to time. So the time variable needs to be in our position equation as it is. So we're good there. We can take the derivative of that with respect to time. First thing they ask for is velocity at 3 seconds. So we're just going to jump in and we're going to be using these as we go to that part C, because they're going to ask for velocity, then acceleration, then net force, all at 3.0 seconds. So let's go. Velocity, we know, is the derivative of position with respect to time. So that's going to be the derivative of 3.0 t cubed plus 2.0 t squared minus 4.0 t. All right, and then that's with respect to time. So here we go. We're just going to take the derivative of that. Remember, we take that exponent, we bring it down front and multiply it by whatever's already there in front. So 3 times 3 is 9. T, and then we take and we subtract 1 from the current exponent, so that's 3 minus 1, which is 2. All right, we're going to take that exponent, bring it down, multiply it by what's in front, so it's going to be 4.0, and we're taking that 2 minus 1, and we end up with a 1 exponent, but t to the 1 is just t, so we're going to leave that. All right, then we get to this next little guy. We've got minus 4.0. That's like saying t to the 1. So we just don't put it there because it's kind of redundant. So we bring the 1 down. 1 times 4 is just 4, a negative 4. But then 1 minus 1, when we subtract it, is going to be t to the 0. Well, t to the 0 is just 1. So instead of saying 4.0 times 1, we're just going to say 4.0. But that 1 is there because it's t to the 0 power, which is equal to 1. All right, perfect. Now we have our velocity. I'm going to keep putting those units because they matter. And now I just put in 3 seconds for all of my times to get my velocity exactly at 3 seconds. These derivatives are very powerful. All right, so now we have 3 squared plus 4 times 3. I'm going to drop that 0.0, but we know there's 2 sig figs there. So our velocity is going to be 89. 3 times 3 is 9 times 9 is 81, plus 12 minus 4 is 89 meters per second. And there's first, part A. Woohoo, check that off. I like checking things off. All right, and by the way, always, if you can remember, it's going to help your graders on your AP exam, your TAs in your engineering physics class. Box these. By the time we get done with these problems, they're like a work of art. Put a frame on it. Helps everybody, saves you some points along the way usually. Okay, now B, we're going to start with B now. We're going to go to B, acceleration at 3 seconds. Okay, well, acceleration is the derivative of velocity with respect to time, or the second derivative, position with respect to time. It means the same thing. I already have a handy dandy little equation here for velocity, so I'm going to say acceleration is the derivative of that velocity with respect to time. So that is 9.0 t squared plus 4.0 t minus 4 with respect to time. All right, well now my acceleration, and I'm getting very sloppy with all my little arrows, and I have been on all my videos, so I apologize. It just saves us time here. So now I'm going to take the derivative of that. I'm bringing that 2 down. 2 times 9 is 18. I take minus 1, that's going to be t, 2 minus 1, which is just t. I have a 1 here, I bring that down, that's just 4.0, and then that becomes t to the 0, which we know is 1. And then this is already like saying t to the 0, I bring that down, and that's just 0 times 4, any number times 0 is 0. So this guy gets dropped off because 0 times 4 is just 0. So now I have I'm going to go ahead and put that in meters per second squared. My acceleration at 3 seconds, it's going to be 18 times 3 plus 4, which should give me an acceleration of 58, I believe, meters per second squared. All right, now that's B, check. Last thing is the easy peasy one now that we've got our acceleration, and that is our force. And I'm going to go over here and do it here, that my sum of my forces equal mass times my acceleration, right? That derivative of velocity with respect to time, which I just found. My mass is 0.5, so my net force is 0.5 times whatever the derivative of velocity with respect to time, which was acceleration, is 58. And I get 29 newtons. Now remember, everything has to be in kilograms, meters, and seconds. So if they gave you milliseconds here, you got to get it to seconds. If they give you grams up here, you've got to get it to kilograms. Because everything in Newton's laws is kilograms, meters, and seconds. All right, that's it. That's how you use the derivatives. Easy peasy, I hope. How you use derivatives to solve some problems with Newton's second law of motion. If you haven't subscribed yet, we would love for you to subscribe. If you have friends that are in this class with you, we'd love for you to share it. And just thank you for watching, and happy physicsing.